Are you trying to do better in organic chemistry? Well, you're in the right spot. We're going to go over directing groups and electrophilic aromatic substitution. Like I said, we're going over directing groups, and directing groups control the site of substitution and electrophilic aromatic substitution, commonly abbreviated as EAS. So, in EAS, when referring to directing groups and the substitution positions, there are three different positions. There is ortho, meta, and para. Now, the names ortho, meta, and para are from Greek, and they're old-timey words when first discussing the substituted benzene, like in the 1860s or something. And you can look up why those names were picked. But basically, just know that they were the old-timey names, and they were just used so commonly that they stuck around and were integrated into IUPAC accepted nomenclature. However, instead of ortho, you could always say 1, 2. That would also be correct. It depends what you want to do. But anyway, so ortho, with respect to our R group, which would be our directing group, ortho is the 2 and 6 position. Meta is the 3 and 5 position, and then para is the 4 position. Just remember, it's always relative to your directing group. First type of directing group are electron donating groups, and those are ortho para directors. They push to the 2, 4, and 6 position relative to our directing group, sometimes abbreviated as EDG. And they also activate the ring. They're known as activating groups as well. So they prime the ring to get it ready for EAS. And they do that by donating electrons. It's pretty simple. They donate into the ring. And here are some common donating groups. And on a relative scale, with this being the weakest side and this being the strongest side in terms of priority and strength, your alkyl, vinyl, and aromatic groups, alkyl groups, are weakly electron donating. And then you have the non-carbonyl side of an amide and an ester. That's very important that it's non-carbonyl side. You have an ester, so like a methoxy. Then you have an OH, an NH, and if you have an alkoxide, um, that's really electron donating. If you notice, a lot of these, they have lone pairs they can inject into that ring, and that's a big key. Electron withdrawing groups function similar to electron donating groups. Instead, they withdraw electrons, just like their name said. Abbreviated as EWG, they withdraw electrons from the ring up into the group, and they favor the meta position, and they're what's called meta directors. And now these are deactivating to the ring. While they favor these positions here, overall they deactivate the ring towards EAS, so it's a lower overall reactivity rate. And there's a lot of different meta directors. You look here, again, this is the weaker side, this is the stronger side. We start with our carbonyls, work our way up to the acid being the strongest one relative to the other ones. Then you have a trifluoromethyl or trifluoromethane. I'm going to say you have a nitrile, you have a sulfur group, an ammonium, and then you have a nitro group. That's really electron withdrawing. So the more electrons it pulls off that ring, the more it deactivates the ring and makes these spots more likely for substitution. There is a special case, and that is our halogens. So like this fluorine right here. So the halogens are very electronegative, and so they're very electron withdrawing. So they're pulling electron density up this ring up to themselves. So they're slightly deactivating in that sense. However, they are ortho-para directors in that they favor these sites, and it's a little contradictory. But what it is they pull electron density off the ring through an inductive effect, but then they have all these lone pairs here, and that donates electron density back to the ring through resonance. So that's why it primes these sites. As always, here's your cheat sheet. Just remember, when you're looking at directing groups, you always want to look relative to your directing group, which is in this case are R. And then there's ortho, meta, and para. Activating groups are electron donators, and they are ortho para directors. Deactivating groups are electron withdrawers, and they are meta directors. Halogens are a special case because remember, they deactivate the ring, but are ortho para directors. All right, hope this video is helpful for you guys. If you want to get some more organic chemistry learning, if you want to do better, if you want to keep doing good, just hit that follow button. If there's any videos you want to see me cover, drop that below in the comments, or you can always send it directly in the DM, and I'll get back to you with any questions you have. If you have a practice problem that you're struggling with, you're not understanding the mechanism, I can go through that too with you or make a video about it.